I believe the answers, or the answers to the problems I gave. Did anybody have any trouble with that? Did you go over it? Yeah, I'm gonna. First, let me do one thing here. Let me complete my thought. It was a reading assignment, sort of, because I had it up to a point, and then I asked you to read, then do it. So I'm going to do two things. So you understand both bilinear and frequency sampling. And then we can work problems out of that. Let's see. Start with that. All right, let me go through it and just give you, bring you up to speed on what we did. We were talking about taking an actual, all right, I took you through the difference between FIR and infinite impulse response filters, right? IR are systems of things that go on forever, technically. Finite impulse response are really truncated, something truncated or something predefined. And so here's sort of the last time what we did. We said that we wanted to use, this would be an ideal filter in the capital omega domain. This is basically it. And we had a filter with this property from minus pi over 2, correct me if I'm wrong here, pi over 2, had a height of 1, and this was h of capital omega. Do y'all remember that class? We took that and we said, well, if that was h of capital omega, then what would h of n be, right? The impulse response. That is h of capital omega. That is the actual frequency response, the transfer function of the system. Are you with me on this class? What I'm trying to show you how to build a real world discrete time filter. So here's sort of the deal. We have a system. This is our x of n or our x of omega. Comes in here, there's a transfer function h, either h of n or capital H of omega. And then coming out here, this is going to be y of n, or sorry, small y of n here equal to x of n involved with h of n. This is easy to do if h of n is defined for a certain number of values, but not infinitely long. It's easy to do. And then we have y of omega, which is equal to h of omega times x of omega. That's the DTFT. You can get that by taking the z transform and just replacing z by e to the j omega, capital omega. Now, with this in mind, if this was a filter for the system, then I know I can get h of n. I can get it, by the way, for this one, we could use duality, couldn't we? You remember how if you were between minus pi and pi, the filter property, and you knew the inverse transfer, you knew the transform, either forward or inverse of that, then we could simply use that to go ahead and get h of n, if we knew h of t for the continuous time. Do you all remember that class? I can go through that. He actually did it by using the definition of how to get h of n. And it's that h of n, really x of n, is simply equal to 1 over 2 pi times the integral, technically from minus pi to pi. I'm going to put that in there to change it. H of omega, right there, times e to the j omega n d omega. You'll need to know this relationship for the final. This is actually synthesis. Do you all remember? There was analysis and then there was synthesis. This is synthesis. So for ours, because our filter has a value from 1 from minus pi to pi, I simply say that my h of n here was equal to 1 over 2 pi times the integral from minus pi over 2 to pi over 2 of just e to the j omega n d omega. This is a rehash of what we did last time. You all remember that? And then what we can do is say that therefore h of n is 1 over 2 pi, and when I integrate this, I get 1 over jn here, then it's going to be times e to the j omega, or e to the j pi
over 2n minus e to the minus j pi over 2n. And you remember my next step, what I do? I think you do. Anybody? Sure. We say that this here is simply 2j times the sine of the argument. Do y'all remember this? I just want to go through it so we're all on track here. So this is gets rid of the j and the 2, so then this becomes sine of pi over 2n divided by pi n. And that is our h of n. But of course, this is something, first, just look at it. Is it causal or not? What does causality mean? Just by looking at this, you can tell. Causality says of what? If the input here is delta of n, my output will be h of n, right? That's really what I'm saying. If this goes in, this comes out. But this cannot exist for a value of n less than 0, because then it would anticipate this. Follow me? Right, it can't do that. So this is non-causal. So the way we make this thing causal is first we truncate it. This is what I did last time. And so forth, I'm going to say for this one, it's going to be for values of n greater than or equal to minus 5, less than or equal to 5, which means the total number of actual values that are going to be used are how many? It's 11. It's going to be what? Minus 5 to 5 has a span of 10, but the 0 is the 11th value, so it's important. That's 11. Now with that, then I take that function there, and I'm going to say this is the only values I'm going to care about. I'll say my h of n here is equal to the sine of pi over 2n, where n greater than or equal to minus 5, less than or equal to 5. That means L equals 11, and it's equal to 0 else. But this is still non-causal because it has values for n less than, even though I truncated it now, so it's something reasonable to use, I still can't use it because even if the delta function happens at 0, this thing still has values back to minus 5, so it anticipated it. With me? So now what we have to do is shift it, right? I'm going to go ahead and shift it first. Then I'm going to go ahead.
Would the, like it being over pi n still carried over to the truncated version? Or
Yeah, I'm sorry. Yes, absolutely. Absolutely. My bad. And it's 0 else. All right. Now, what I have to do is I have to shift this thing so it starts at 0. So now I'm going to shift this entire function here. Actually, the way the book does it, I'm going to explain something. What the book says is right there, we're going to start with that, but then I'm going to pick a window. Now remember, the window has to start when the function starts. Here the function starts, the h of n starts at minus 5. So we're going to take the window, and I'm going to tell you don't have to do it this way. I'm going to show you a trick here in a second, but I'm going to do it the way the book does if you read it to make sense of it. So if I take this here, it starts at minus 5. I'm going to apply a Hanning window. This is common for almost any type of filters because anytime you do this truncation business, you know, where you have a filter response and you truncate it, automatically, if you don't do something, you get these side lobes that are unwanted. You're going to get things that are unwanted in the frequency domain. All right, class? This is the reason I'm doing it. So now I'm going to take the typical Hanning window and multiply it by this but I have to adjust the Hanning window. So the Hanning window, W sub h of n, is equal to 0.54 minus 0.46 times the sine of 2 pi n over L minus 1. This is what the window is, and this is for a function of length n. Y'all remember that? Now this window, if you just look at this, or I'm sorry, this is cosine, my bad, cosine right here. If you just look at this function here, well, what's the value of this function at 0? I mean, when n is 0. Well, what's the value of cosine of 0? 1. So I got 0.54 minus 0.46, that's very small, right? It's something that's, you know, really, it's about 0.08, right? It's something less than a tenth. But then, as you go through and transition, the cosine will go to 0 when the argument here is pi over 2. And finally, when you go all the way up, this becomes minus 1. The cosine will be minus 1. Minus 1 times 0.46 will bring this to a positive 1 value. Follow me on this, class? You get 0.54 plus 0.6. So this is one of those functions, if I drew it here with the window, it starts like this, and it's basically like this kind of a window, if you take a look at it, right? So I take this, and now I have to shift this. See, this is going to be valued for n greater than or equal to 0, less than or equal to L minus 1, and I've got to shift it back to where this starts. That starts at minus 5, so I'm going to take n minus 5 here. This is how he does it in the book. So I'll call it Wn, he put a little hat here at n, and that's 0.54 minus 0.46 times cosine here of 2 pi, but not n, now it's going to be n plus 5 over 10, because here L is 11. Now, this is the way the book does it. I'm going to show you something. You don't have to do it this way. What he's showing you is the way it's usually done. You take the window you're going to use, and then you shift it to the actual, my left here, looking at the board. You want to shift it so it starts now at the proper time, at minus 5. Got it? So I add 5 right here. Follow me? Now by adding 5 to this window, I'm going to take this function right here, and I'm going to multiply it by that. Then I'm going to shift the results back over, which effectively negates what I'm doing here, by the way. But there's a nice little thing that happens when you do this. So this window here, Hamming window, it's actually got the hat on it because it's adjusted, is 0.54 here, but I want you to notice what happens here. This is 2 pi n over 10, right? So that's really pi over 5n, right? But then you've got 2 pi times 5, or 10 pi over 10, or simply plus pi, don't you? Let me go ahead and write this. So this becomes minus, I'm going to just do this so you see it right here. It'll save me some time. This is really pi over 5n plus pi, right? What happens to a cosine waveform when you add pi to it, 180 degrees? That's minus cosine, right? The minute you add 180 degrees to the value of a cosine, you get minus in front of there, right? And you can just get rid of that pi. So this is going to be now 0.54 plus 0.46. And then it's going to be cosine of simply, you can put 2 pi in if you want over 5. I think he does leave that there. You don't have to, but 2 pi n over 5 here. Over 10, pardon, over 10. Now, this is the window that now is adjusted, and it's good for n greater than or equal to minus 5, less than or equal to 5. Now I take this window times that function, and I'm going to do this. You'll see that there's a shortcut to this, but I need to go through this because this is how the book lays it out. And in general, this, I believe, is how it's done when you do filter design. Dr. Reeves would actually be the person to talk to you about this. So now I'm going to take that modified Hamming window and multiply it times h of n. And now I'm going to get my actual, he calls it h, well, this is not quite adjusted. It's h tilde of n. It's going to be the sine of pi over 2n, and then it's going to be divided by pi n, and it's multiplied by that window, which is then 0.54 plus 0.46 times the cosine of 2 pi n over 10. But this is still n greater than or equal to -5, less than or equal to 5. Don't ask me. I just work here. Any idea?
We opened the door a little.
No.
I think they're doing a high school football game.
It sounds like a national anthem.
Yeah.
Well, whatever it is,
Going
we
high
keep
school
going.
football game.
Listen, here's the bottom line. I gotta shift it back. Everything started at -5. That doesn't make sense. It's still the delta function response. Now what I need to do is shift everything by 5 to the right. Following? And that means I subtract 5 from n. So now this is a real important part. Now this is going to be h tilde of n. And this will be the h response that I'm going to use. I'll call it h hat. Equals. And this, when you do this, this is the important thing. This becomes sine of pi over 2 n minus 5 pi over n minus 5 times, you ever go to an opera?
Well, now I have.
If you get a chance, go at least once. You'll be surprised how that reminds me of an opera I heard. It was in Italian. I don't speak Italian, but somebody in here does. They would appreciate it. All right, then this becomes 0.54 plus 0.46, and then you put n minus 5 here, right? Effectively, you cancel what you just did to this. In the book, the person doesn't say that. So now we can just go back to the original function, the window. Did anybody notice this, by the way? All right, look, I didn't write the book, but I'm going to tell you why I did it that way. Because a lot of times when they modify windows like this, all right, they actually take the windowing function and they'll move it back until it fits squarely over the function, the impulse response that's not causal, and then they'll just multiply it out there, and then they'll shift everything. All right, and I know this sounds wacky, but it's sometimes not just one window that they use, and they want to get all the windows shifted to the point where the impulse response is actually recorded. Some of these things are driven by a lot of other things other than a simple response like this. We assumed it was a nice square thing, we're just taking a window on that. It can be an actual ripple effect and stuff like this. What he did in the book is something that is actually done. So this becomes minus 0.46 times cosine, and then it's going to be 2 pi, and minus is back, 2 pi n over 10. And that is, in fact, the impulse response to this. Now, listen, this is good for n greater than or equal to 0, less than or equal to 10, right? We're going to actually talk about the results in the book. Does anybody see one thing that might be problematic if you tried this in MATLAB? Yes, Josh.
I was just gonna say it's time shifted, so the output is gonna lag.
That's right. The actual output itself is going to have a delay of n of 5. N times 5 times the actual TS, the sampling interval. That's the first thing. The second thing, take a good look at that. What could be problematic? Just think, just for a second. And 0, and 1, and 2, and 3, and 4, and 5, and 5. Look at n equal 5. Where do you see a problem?
Gonna have a vote.
Right here. When n equals 5, this is 0. Now you have to evaluate this using L'Hopital's rule. Take the derivative of the top, derivative of the bottom, and evaluate that at the singularity. In truth, the only thing you have to bring out is a value of 1/2. So you have to define it at n equal 5, the filter response. This part of the filter response has a value of simply 1/2. Understand, class? Everybody with me on that? You don't use this. At n equal 5, that's 1/2 times this. Got it, class? And that's important. Because if you write a MATLAB code, you're going to get error after error after error until you do that. You understand what I'm saying here? And why it's important? And you can do that. By the way, all this stuff right here, now I want you to just know this. This has values for what? N equals 0 through 10, 11 values. You can store those 11 values in a vector. Just calculate it one time, store them in a vector. Now you You can involve the heck out of that within input, and that's it, that's all you need. So, when I come down here and I have this, when I adjust for the n equal 5 problem right there, now I can calculate these values and store them, right? Did you actually try to do this or not?
I followed along in the book, I'm just laughing.
Oh,
It keeps going.
Pavarotti out there? Yeah.
Yes, it just keeps building.
Can you tell what they're saying?
It
No,
sounds
I
like
want
God
to
bless
open up
America.
the doors and try and hear.
I don't know what they answered, but it's been going on for like 10 minutes now.
If it's in Italian, you can tell me what it means. But I don't know what language he's speaking out there.
Yeah. That's what it
high
is.
school football thing that's supposed to
Oh,
go on.
that's on.
I started today.
We could sample
No, we're not. Enough.
one pass filter to filter out the noise.
Oh, God. Needs construction, all right? There's a comic element
I
to this.
prefer the high-pitched beeps.
All right, let me just tell you this. You understand you can get 10 values out of that and store it? And for n equal 5, you need to calculate, this one is 1/2 times whatever that is at n equal 5, what do we actually have? We have 1/2 times still reciprocally cosine of pi, which is -1, right? -1 times the minus 0.46 is plus 0.46. You add these two together, you get 1, right? So at n equal 5, it's 1 times 1/2, or it's 1/2. So you already know that value. You can put it in. And then once you get this, this will become a vector. You're going to have h equal, and it'll just be a vector. And they're going to have 10 values. Now, when you have that, if you want the output for any input, MATLAB has a function called CONV. Have you seen this? Has anybody used this before? You can take any two vectors and convolve them, any two vectors at all. And you can do convolution where it's a sort of a moving average regressive filter where you can take it and you can involve real-time information. Every time a new bit of data comes in, you can convolve it, get the output, convolve it, get the output. So in the book, what he does is he gets this vector length here, and then he shows a real-time waveform. If you actually look on page, I think it's 495. Correct me if I'm wrong. I was going to have you do this. Let me just show you. So we're going to be able to store all the values for n equals 0 to 10 here into a vector. Really, we're going to have 11 values here. It's bottom line on that. We have 11 values. Now he says consider two signals. And he's going to say his x of n here is actually equal to cosine of 0.2 pi n plus, and then it's going to be cosine of 0.7 pi n. Do y'all remember reading that in the book or not? Do you remember this, Josh? On the page? Do you have your books with you, anybody? On page 495, do you see that? Now, he shows this. Remember, this is sampled at discrete time. He actually shows this. I can put it up, it's in your book, and he just shows you it's sort of erratic kind of thing like this, but you can see there's some periodic behavior. It's sampled, so obviously these are lines going up like this. But it's erratic, hard to see what's going on. He has two cosine waveforms, right? And this one, is it more than 3 times this frequency? But you remember the original filter, when we looked at this, I wanted the filter properties to be 1, this was the original h of omega, and 0, anything out of that band, all the way up to pi, right? Now that means, if you look at this, the 0.2 pi is right there, right? It would also be a minus 0.2 pi. Well within the pass band. That should pass, correct, class? But then there's the 0.7 that's up here. That one shouldn't pass. And indeed, when you take this, right here, then you can create this, you can create a vector, say n goes from 0 to maybe, I don't know, 700, something like this. You pick a value, something large. You take that, now you're going to get a data record for all these things, 701 entries, say, all right? Now you can take that, and with MATLAB, you can do the convolution function. You can say y is just going to be equal to CONV, because these vectors don't have to be the same length, of vector x, comma, vector h. And then the output y will be a time domain signal. It'll be delayed by 5, remember that. But then on your output, you'll see the operation of the filter, and it gets rid of this just about all the way. Now that's on page 495. How many have your books? Do you see it there? Or is it? It's
494.
494. 495 has the actual block diagram. We see the sampled signal at the bottom of the page with both waveforms, the cosine of pi, or I mean 0.2 pi n, plus the cosine of 0.7 pi n. And then he shows you, after doing the convolution down there, how the filter got rid of the unwanted one. Follow me? Now I want to tell you something. The filtering technique that we used was effective because we did this windowing thing, still effective. If you don't do that window, you won't get those results. You'll see the second waveform still fairly apparent. But that window, did anybody do this, by the way? Try that. Does he have the CONV code in there or not?
I don't see it.
I'll put it up at the end of class 5 time. I'm going to put it up. Now, so what are you responsible for in terms of this for the final exam? I gave you several problems, and I'm going to go through some of them. The representative stuff, it doesn't have to do with MATLAB programming, but actually creating this right here, using a window and using a shift, based on the fact that we had this filter, right? This h of omega. From there, we got the h of n. Then we truncated it, right? Symmetrically truncated it. And then what we did was take that and multiply it by a shifted window, a Hamming window. I don't expect you to memorize Hamming windows or Hamming windows or Bartlett's windows or any of those things. I would always give those to you. But you have to be able to shift them yourself. And I wouldn't do anything more than a shift of 5, something like that, something reasonable. Then, and I wouldn't ask for singular values. I just want to see the mathematical operations. Then once you have this right here, then what you can do, I mean, you can generate those points and simply do a convolution to get all values of output y right there. And I'm going to tell you right now, it's going to have 5 extra values in the input because it is time delayed by 5. That's the one thing and the only thing that we really care about. Everything else is right. It's the correct impulse response. And it's amazing how good this kind of a filter works. Because in the analog domain, to get a filter that is this effective, you're talking about active elements, you'll see this. There are things that require a more finesse than I care to talk about right now, but that's later on in the development. You'll be getting into filtering where they talk about using active operational amplifiers and developing Butterworth filters and things like this. Now, the first filters, just RC and LR filters, they have a maximum reduction rate of 20 dB per decade. If you had an L and a C, and say a low-pass filter, where you had you wanted a low-pass filter where you put a capacitor. Let me just tell you what I'm saying. This has got a reduction of like 50 or 60 dB per decade, which is phenomenal. And it's a very easy filter to build. I believe it's that much, but I didn't actually check. But what's the dB reduction in what we tried to do right here? It's going what? From as many, pick a number there, all right? From 0 dB to minus infinity dB instantly, right? It's got a roll-off it's greater than anything you can achieve. If you actually look, take that impulse response right there, that we did, the truncated one, do the Z-transform and plot it, what you should actually get is this. You're going to get something that does, flatten it, there's an overshoot and comes down, but the window gets rid of that, and it's basically like this. It's a very, very good, it does have a slope, but that's like 50 or 60 dB, yeah.
Is that kind of like when we were doing the Fourier series and we had like the overshoot because we had like a finite number of cosine?
You're talking about the Gibbs phenomena.
Yeah.
That's different. Gibbs phenomena, doesn't matter how many terms you get, you're always, wherever there's a discontinuity in time, if you try to develop a Fourier series to represent a periodic function, you're gonna always get that overshoot and undershoot and ring down. It doesn't matter how many more terms. The more terms you get, the shorter the interval of the ringing is.
Right.
But you still get that overshoot, you cannot help it.
But is that?
No, that was Gibbs phenomena. This is different. This has to do with the finite numbers causing. If we had an infinite h of n, then we get ideal. Follow me? But it would have to go from minus infinity to plus infinity. Then you get the square. But that's non-causal too. It is very interesting how close you can get though to that with just with 11 terms. Now, if you want to break that out to be like 50 to 100 terms, you can get an amazingly good filter. But then the convolution is going to be delayed by that many before it starts, before the output's reasonable to use. So that's another thing about real-time systems. You don't want too much delay. All right. Anyway, we took the h of n, we truncated it, then we multiplied it by a shifted window, a Hamming window in this case, then took the whole thing and shifted it back. He didn't have to shift the original Hamming window, but he chose to do that. And then once we shifted it back, that is the h of n we use for convolving. The thing about it is you have to watch for the singularities whenever you do this. And at 5, you have a singularity. Then you have n minus 5. Follow me? Because anytime you shift, and there's an n on the bottom, on the denominator, where you have an n minus 5, n minus 6, something like that, that's where you have to evaluate that one separately. And that's really the bottom line of this. Now, the next thing with filtering, this is, we did bilinear, we talked about this. Now, there's also frequency sampling, sorry, I'm not going to do frequency sampling right now. I'm going to do time domain sampling, because this is actually what he talks about. So if you had an actual filter, let me just show you this, and show you how to take these values. This one you'll like, because it's very easy to understand. And we could apply a window to it. So, suppose we had a circuit like this. Add an R and a C circuit right here. And this is my input. Call it X of T. Here's my output. Y of T. Right? And I want to get the impulse response for this. I'm going to do this using Laplace transforms. That way we'll keep everything at t equals 0 or greater than 0. So if we're going to do this, this C has an impedance of 1 over SC, right? And then if we wanted the impulse response, really we want the ratio of, call it X of S, and this would be a Y of S. We want Y of S over X of S. So when we look at this, Y of S over X of S equal to H of S for this is really what? Isn't it just this impedance over the sum of this impedance plus that impedance? Right? That's the ratio of Y of S to X of S. So you can say it's just 1 over CS over 1 over CS plus R. Now, I'm going to first multiply top and bottom by S. So that will become 1 over C. This will be 1 over C plus RS, right? And then divide by R. So that gives me 1 over RC here over 1 over RC plus S. Does everybody understand what I've done here? And that is my H of S. Correct? Now, to get my H of T, that's the impulse response to this. Remember, I used Laplace, not Fourier for this one. What is the impulse response? Isn't that really just a constant over a constant plus S? What's the Laplace inverse Laplace of that? What does e to the minus at u of t go to, class? In Laplace domain. 1 over S plus A, right? What if I multiply this by A, what happens? Other side, just A, right? Now, you see how A is 1 over RC? All right, so this is simply going to be what? 1 over RC times e to the minus T over RC times U of T. Do you all agree with that? Come on, really. I'm trying to help you. This is actually something I'm doing on purpose because the final exam is going to have stuff like this on. You're going to have to recognize both the forward and reverse or inverse Laplace transform properties. They're the simple ones, not hard ones. Do you all see this? All right, now listen. If you want to take this information first, this exists for all time, right? We could say the infinite impulse response, the IIR filter, impulse response of this filter, would be H of, and you let T become NTS, where TS is simply the sampling interval or time. It becomes NTS, and then let me put it over here. Then you get your H of quantity NTS, I'll suppress the TS in a second, will become TS right here, and then it's going to be times e to the minus NTS over RC times U of N. Now, what I've done is, I'm sorry about this. What I should say is, what you actually do is multiply by TS out in front and then replace anything in the inside here in the functional form by NTS. This is shown in the book if you look at this. Did anybody look at this or not? In other words, what you have to do is this. First, you replace all T values with NTS. And then after doing that, you multiply the whole thing by TS. That's what you have to do. Yeah?
But you still have the 1 over RC up front?
Yeah, you will. You will. But the TS has to come out in front. No matter what the functional form is, there's going to be TS times, then inside the H of T, that T is then turned into simply NTS, but there's a TS outside of that. Now that's shown in the book. Did anybody notice this in the book when you're reading? Now, still, if you look at this, if you actually plotted this, it has the same exact form as the original one, except it's weighed by TS, right? Same exact form. It's a sample version of that signal, but it's weighed by TS. But this goes on for n greater than or equal to 0, less than or equal to infinity. And here's the one thing. Just like in the prior one, in order for this to work, you're going to have to take a finite number of samples. So, what kind of filter is this, by the way? Take a look at it. Just look at it here. Simple. Is it high pass, low pass, band stop? Pardon me? You all see it's low pass? Here's how you can always tell. Just look at what the output of this is going to be as frequency goes to 0. You know, a capacitor has an open circuit. It looks like an open circuit for 0 frequency or DC, right? If that's an open circuit, the input is the output, right? What happens to this as frequency goes to infinity? What's the impedance of this? It's 0. And therefore the output would be 0, right? Divided by 0 plus something times the input, or it would go to 0. You can just take a look at that. That's a low-pass filter. Do you understand that, class? If that's a low-pass filter right there, and you look at this stuff we just got here, you realize if we take a finite number of points here, it would be something that would do a low-pass filtering operation on your input, right? Do you all agree with that? Now here's the one thing about this one. If you just looked at this filter right here, or this filter, the 3 dB point, the point where all of a sudden the output will be 70% of its maximum value on this filter, will be when S equals 1 over RC, or where the magnitude of J omega equals 1 over RC, or omega is 1 over RC. Do you follow me on this, class? Yeah, I mean, I'm not gonna go into too much more about these filters. But when all of a sudden you do it in the sample domain, right here where you have MTS, now for this filter right here, in the frequency domain, it would be magnitude of omega equals 1 over RC, or simply F, magnitude of F, is 1 over 2 pi RC. And this would be the 3 dB frequency, right here. So if you're plotting the filter output from 0 to F 3 dB right there, that's where it starts coming down, and then from then on, you're getting 20 dB per decade of roll-off, if you did a Bode on that. However, when I look at this omega, that corresponds to capital omega divided by capital TS. So if you wanted to know where it was in the capital omega domain, you'd multiply that by TS, or you'd multiply TS times 1 over RC, and that would be the 3 dB frequency in the capital omega domain. Follow me in this class? Remember, this is sample. So now the domain we're in is the capital omega domain. And that means the omega 3 dB, I don't expect you to know this by heart, but that would be simply TS over RC, and that would be for the capital omega domain. Follow me? Go ahead, Josh. Remember, omega TS, small omega times TS is capital omega, where TS is the sampling level. Do you remember that? Kind of, sort of?
Yeah.
All right, don't worry about this much of it. What I'm really getting at, when you have this, how many dB of roll-off was that? 20 dB, right? Now think about this. I can adjust the value of RC here so that the 3 dB frequency would be the same as the frequency we had for the original filter. The frequency I had in the omega domain for that was what? It was pi over 2. Do you remember that? That's for capital omega, right? Capital omega is like small omega times TS. Now, for this one, the 3 dB frequency would be TS over RC. But the thing is, when you take this filter output, sampled right here, this is 20, and you take, say, 11 points here, just 11, if you try to do this without a window and do convolution of the original signals we had, we could adjust it so that the 3 dB frequency would be, in fact, pi over 2. You'll find out, this is the bottom line, if you took 11 terms here and you did convolution, just like we did before, you would still very clearly see the 0.7 pi n signal, cosine of 0.7 pi n, where the original filter we did got rid of it completely, just about. I mean, there's a little risk. This method is easier to use because you can, that's a 20, we can get I'll show you a filter with 40 dB in a second. We can get this, even 60 dB, but the problem is, for this thing to really work, you don't need 11 samples. You're going to need maybe 100 samples, and it still wouldn't be as good with the convolution as the one we did originally, where we took an ideal filter in the capital omega domain, got the H event for that, and then went ahead and multiplied it by a window and shifted it. That would do much better than this, is really what I'm getting at. And I don't expect you to know that much about this, but this is what he's talking about. Now, in the book, let me do that problem real quick. Which one did you want me to do? Which one? Because that's what he's talking about with the frequency sampling. When he's talking about, what's the term he actually uses? Impulsive something? I didn't do the frequency sampling one. But there are a lot of ways to do this stuff. Which problem was it? Last two. Can you give me the specs?
It says it gives H of A S.
H of A.
H8 of S equals 1 over S plus 1 squared. When T is equal to 2. And it says design.
TS?
It just says T equals 2.
All right.
Design digital filter using impulse invariance.
All right. And what else?
That's it.
There's a second bilinear to it.
And then bottom here.
Well, the bilinear is the one we did, right? Right? And it has both in there, right? So if you're going to do this, first, if you're going to do impulse invariance, that's the one I just did. All right? If I showed you this, what do we need first for that? If this is H, capital H of S, right? Sorry. And T is 2, then what is my H of T? Take a look at that. HA of T. Well, what if it was 1 over S plus 1? What would the output be in the time domain? E to the minus T, U of T, right? What if it's 1 over S plus 1 squared? Hint. T times, right. This would be what? It would have T times what? E to the minus T, U of T. Correct, class? Isn't that right? All right, now for what he says, impulse invariance. This is the impulse response, right? Now we take this and we first replace T by NTS. So now I say my H of A of NT here will be simply NT here times E to the minus NT times U of N. Just U of N because the T adds nothing to it. When N is 0, it's on, or greater than it's on. The TS times that doesn't do a thing with me. But now I have to take this whole function and multiply by T also. And that should be in the book. Do you all see the answer to that one? Who asked me this? You did? Do you see that? Take a look at the solutions. Don't you have it?
Yeah.
You see how he did this very thing? This is for impulse invariance, right? All right, now how do we do the bilinear on this? Remember, this is one not yet, actually I did show you some of this last lecture. What do? We take S and we do a conversion to Z, right? So we first say that, now we're going to have what? S will be equal to 2 over T times Z minus 1 over Z plus 1, right? Y'all remember this? You remember this right here? Really, it was what? It was natural log of Z over T, but we did the approximation where natural log is 2 times Z minus 1 approximately over Z plus 1. All right, now pay attention to this. That's S, right? So I come over here, and I say now my H of S is no longer S, but it's going to be Z. And now I take 1 over quantity, 2 over T times quantity Z minus 1 over Z plus 1. I hope he shows this in the book. Plus 1, we have to square the whole thing. Don't we, class? Right there? Keep watching. If I'm doing that, what happens? Well, there's a couple things I can do. I mean, I can simplify it a little bit. If I'm doing that, if you want to just brute force it, what do you see you get? Well, you're going to have what? 1 over the quantity, 2 over T, right? Z minus 1 over Z plus 1, right? It's going to be that squared. Then it's going to be plus 2, or really 2 times this, or 4 over T, times Z minus 1 over Z plus 1. And then you're going to have plus 1. In other words, I simply went ahead, took this and squared it, multiplied this times 2, and put it there so you get 4, and then I took this and squared it, or plus 1, right? Now if I get that, and I want to keep on going, before I put Z equals J omega, J capital omega, what might I do? Take a look at that. I think the easiest thing to do is multiply the bottom one and the top one by T times Z plus 1 squared. That will get rid of this. It'll put a T times Z plus 1 here, which will cancel that, and then you get a T plus Z plus 1 squared here. Follow me? So if I multiply top and bottom by T times Z plus 1 quantity squared, so I'm multiplying top and bottom on it. So let me do it up here. Then you're going to get, just let me finish this. T times quantity, and then it's going to be Z squared, right? Plus 2Z plus 1 over downstairs. Now I get 4, and it's going to be Z squared minus 2Z plus 1 here. Then what happens to the next part? Then I get 4 times the quantity z minus 1 times z plus 1 here, don't I? And then you're going to have to add this term right there, which is going to be, I needed a t in here. Plus the quantity p squared times z squared plus 2z plus 1. Are you with me? Now that I have it down to that point, you all see that the highest power downstairs is z squared, right? I can group the coefficients of z squared. I'm going to have a 4, I'm going to have another 4, and I'm going to have a t squared. So I got 8 plus t squared. I can group with z squared. For z itself, I can group the coefficients. Do you all agree with that? And then for just the constants, I can put them up there, same on top. Now, after you've done that, then you replace z by e to the j omega. Are you with me, class? And now you have, in fact, the filter property. That is the actual filter h of omega. Correct, class? And then if you have that, if you wanted h of n, you can go ahead and take 1 over 2 pi, the integral from minus pi to pi of that h of omega times e to the j omega n d omega, if it's a feasible integral. Or what you can do is right here, do an inverse z transform of that. This is maybe easier. Did he do an inverse z in this book to get that? Inverse z? That'd be easier probably, but either one will work. And you can get the filter properties by doing what I showed you there. All right, Friday I'm going to do a big wrap up on all this stuff. I gave you, what, two homework problems or 3 last time? 2? Did you do them? I hope they made sense to you. I'll go over those more on Friday. I needed to get through that impulsive technique.
Is there a quiz on Friday?
I'm not going to do a quiz this Friday because this is a big wrap up. And when's our final? At what time? Wednesday at 12? 12. What?
No, I just said AM, 12 AM.
Somebody shows up here at midnight. That is. All right. I enjoyed this class. We're not quite done, but we've done all the material.